Hello all, welcome to Tungal online classes. Now in this session we will see hysteresis, hysteresis curve, permanent magnet and ferromagnet. In detail we will see. In the previous class already we have seen the ferromagnetic materials. In ferromagnetic materials, the magnetic dipoles are arranged in a small region such that all magnetic dipole moments has same direction. That region we are calling domains. And the ferromagnetic material, it is strongly attracted by magnetic field and it has lot of the properties. Already we have seen what is magnetization in case of ferromagnetic material, magnetic susceptibility, and a ferromagnetic material placed in an external magnetic field, it moves from weaker region to stronger region because it is strongly attracted by magnetic field. Then today's concept is hysteresis curve. Here meaning of hysteresis curve is mainly this is property of a ferromagnetic material. When a ferromagnetic material subjected to series of changes, it has interesting properties. Those interesting property we are calling retentivity and corrosivity. In detail we will see what is hysteresis curve, what is meaning of retentivity and corrosivity. Right students? Now to understand the hysteresis curve, we will take a ferromagnetic material. Right? Shall I take a ferromagnetic material? Initially I will take a ferromagnetic material. Remember this is ferromagnetic material. Ferromagnetic material. When ferromagnetic material placed in a current carrying solenoid, shall I take a solenoid? How it is? So the coil with many number of turns, this we are calling solenoid. Remember this ferromagnetic material, say iron, it is placed in a current carrying solenoid. Right. I said that hysteresis is a property of ferromagnetic material which is the relation between magnetic intensity and magnetization. Magnetic intensity and magnetization. How magnetic intensity changes, in what way magnetization of the ferromagnetic material will change. That phenomenon you will see here. Remember, so initially we know that whenever no current can flow in the solenoid, current is 0. Wherever current is 0, so let us take current equal to 0. Wherever current is 0, this ferromagnetic material never magnetize. I mean no magnetic moment can develop in it. Wherever no magnetic moment can develop, then what you can call directly? See here. So wherever no current is there, then what about this B value? Magnetic induction 0. Wherever magnetic induction 0, then what is magnetic intensity? This magnetic intensity also 0. Wherever magnetic intensity mean what? External magnetic field which magnetized the material. Right? So initially I said that wherever no current is there, no magnetic induction in this material. Wherever no magnetic induction, magnetic intensity also 0. Right? Then when magnetic intensity is 0, then no magnetization exists in this material. Directly magnetization of the material mainly depends on magnetic intensity. What is magnetic intensity here? External magnetic field which magnetize the material. See here, I said hysteresis curve is nothing but the relation between magnetic intensity and magnetization. See here. Now I will take a curve. How to take? Along x-axis I will take magnetic intensity. Along x-axis I will take magnetic intensity, and along y-axis I will take magnetization. What I will take? Magnetization. Remember this. See here. So along x-axis I will take magnetic intensity. Along y-axis what I will take? I will take magnetization. In some other book they will take magnetic induction. How magnetic induction will take and how magnetization will take, that we will see. Either can take here magnetic induction or magnetization, both are the same. So how it is same, that I will explain later. Remember, so along x-axis I will take magnetic intensity. What is magnetic intensity? External magnetic field which magnetize the material. And this is property due to this external magnetic field, magnetic moment developed per unit volume, that we are calling magnetization. What we have seen? Whenever no current is there, no magnetic intensity. Wherever no magnetic intensity, magnetization also zero. Where it is represented? When magnetic intensity and magnetization both are zero, then it is represented by quantity what? Represented by quantity O. Right around. Now I want to increase the current in one direction in a given solenoid. How it is? See here. Now see here. When current increases in one direction in a given solenoid, when current increase, magnetic field lines also increase around current carrying solenoid. I mean magnetic intensity developed in the current carrying solenoid. Magnetic intensity developed in the current carrying solenoid. Wherever magnetic intensity developed in this ferromagnetic material, it get magnetized. It get magnetized. Magnetized means it acts as a south pole and a north pole. So it get magnetized along the direction of applied magnetic field, so that magnetization can develop in it. Right? How magnetization developed as a function of magnetic intensity? That is question. See here. Initially, when magnetic intensity increase, magnetization also increase. How to show? So graphically it shows that the magnetization and magnetic intensity, they will changes along this path. Changes along this path. I mean, how much magnetic intensity increase, so magnetization of the ferromagnetic material will increase at a particular point. At a particular point, if magnetic intensity increase, there is no further increase in magnetization. See here. So at this point the magnetization remains same if we increase the magnetic intensity. So this point we are calling saturation point. Saturation point means at a particular value of applied magnetic field, all magnetic dipoles exactly aligns parallel to direction of magnetic field in such a way that there is no further alignment. What is physical significance of this saturation point? At a particular value of applied magnetic field, all the magnetic dipoles in a ferromagnetic material, they exactly aligns parallel to direction of magnetic field. Hence, there is no further magnetic dipole moment there is no further magnetic dipoles remain to align along the direction of applied magnetic field. So, at this point what happened? All the magnetic dipoles, they exactly aligns parallel to direction of magnetic field. This point A we are calling saturation point, and this curve OA is called initial magnetization curve. Shall I call it? So I can call the curve OA is nothing but initial magnetization curve. Initial magnetization curve. Initial magnetization curve. Initial magnetization curve. Right? Now I want to decrease the current in a given solenoid. How the current increase? The current increase in one direction. Now what I will do? Just I will decrease the current. Wherever current decrease, the curve should be along AO, but it should not happen. Instead, when current decrease in the solenoid, the variation of magnetic intensity and magnetization, they will follow the path. They will follow the path along AB. How they will follow? So, if we decrease the current in the given solenoid, the change in magnetic intensity and magnetization, they will follow this path. They will follow the path AB. Instead, the path AO. At a particular point here, in this case, magnetization is not zero, but magnetic intensity is zero. Magnetization not zero, but magnetic intensity not zero. What is meaning of this? At a particular point, if we decrease the current, even in absence of external magnetic field, the material behave as a magnet. This property we are calling retentivity. What is retentivity? Even if you remove the external magnetic field, the ferromagnetic material shows magnetization. That property we are calling retentivity. Here what is the property of retentivity? See here, at the point B mean this region OB, we are calling retentivity. This we are calling retentivity. Look at me, what is meaning of retentivity here? Retentivity mean the property of ferromagnetic material, it shows magnetic induction or magnetization even in absence of magnetic intensity. That property we are calling retentivity. Actually, H is equal to 0, then I is equal to not 0. In absence of this field, even this ferromagnetic material shows magnetization. This property we are calling retentivity. And the retentivity can be shows along what line? Retentivity can be shows along the line OB. See here, I can define the term retentivity. Retentivity is what? The property of ferromagnetic material. The property of ferromagnetic material. Property of ferromagnetic material. Property of ferromagnetic material. Magnetic material. Property of ferromagnetic material, which shows magnetization. Which shows magnetization. Magnetization in absence of magnetic intensity. In absence of magnetic intensity. So this property we are calling retentivity. Retentivity means if you remove the external magnetic field, again that material shows magnetic field lines in it. That property we are calling retentivity. I mean, at the point B, the material behaves as a magnet if you remove the external magnetic field. Right? Now I want to remove this property. I mean, I want to remove the magnetism of the material even in absence of external magnetic field. Then what I will do? Now I want to increase the current in the solenoid in reverse direction. What I will do? I want to increase the current in the given solenoid in reverse direction. If you increase the current in reverse direction, it will follow this path. So at a particular point, how it follow the path? It follow the path BCD. At exactly C point, look at this point. At this point, magnetic intensity is 0, but magnetization is 0, but magnetic intensity is not 0. I mean, to demagnetize the ferromagnetic material, I increase the current in reverse direction. Whenever current increase in reverse direction at a particular point, say C, magnetization is 0, but magnetic intensity is not 0. This property we are calling corrosivity. Corrosivity means the reverse magnetic intensity required. I applied reverse magnetic intensity. This is forward magnetic intensity, this is reverse magnetic intensity. The amount of reverse magnetic intensity required to demagnetize the material. Actually, at this point, the material behaves as a magnet even in absence of external magnetic field. Right or wrong? Right? See here material acts as a magnet, but in this case, material becomes demagnetized. So, this property, this point C, what you are calling corrosivity. See here, C point. The C point we are calling corrosivity. What is meaning of this corrosivity? The reverse magnetic intensity required, the amount of reverse magnetic intensity required to demagnetize the material. That property we are calling retentivity. How it is? The reverse magnetic intensity required. Reverse magnetic intensity required. Reverse magnetic intensity. Reverse magnetic intensity. Intensity required to demagnetize the material. Required to demagnetize the material. Demagnetize. So this property we are calling corrosivity. I mean, at this point material act as a magnet even in absence of magnetic intensity, but if you apply the reverse magnetic intensity by increasing reverse current at a particular point, the material becomes demagnetized. So that again, if reverse current increase at a particular point, all magnetic dipoles aligns anti-parallel to direction of magnetic field in such a way that further no magnetic moments are remain to again align parallel to direction of magnetic field. Again, this point I can call saturation point. This point I can call saturation point. This point also I can call saturation point. So here all magnetic moments are aligned exactly parallel forward direction. All magnetic moments are aligned exactly parallel in opposite direction. Right thing. Now again I want to decrease the current. Again I want to decrease the current. Wherever current can decrease, again it follow this path. How it follow? So it follow the path C D E F. D E F. Again, if current is decreased at a particular point, again at this point again what value? Again I is not 0, then what about H? H is equal to 0. So again at this point material get magnetized. I mean this property what you are calling retentivity, this property I can call retentivity, this property I can call retentivity. Again at this point F fine, at a point again what value? Again I is equal to 0, then H is equal to not 0. This property what you are calling? This property we are calling corrosivity. Right, or if you decrease the current, again if you increase the current in forward direction, how it goes? Again it goes this way it goes. So that when a ferromagnetic material subjected to external magnetic field, it get magnetized, it get demagnetized. Where does get magnetized? So at this point B and at point E it get magnetized, and at point C at point F it get demagnetized. So this loop we are calling hysteresis loop, and this cycle we are calling magnetization cycle. So what is magnetization cycle? Magnetization cycle indicates that when ferromagnetic material subjected to series of changes and brings back to its normal state, so that cycle we are calling hysteresis cycle. A ferromagnetic material subjected to series of changes and brings back to normal state, this we are calling hysteresis cycle, or this we are calling magnetization cycle. And this loop A, B, C, D, E, F, A, this we are calling hysteresis loop or hysteresis curve. Which loop we are calling? The curve A, B, C, D, E, F, A. What are calling this? Hysteresis curve or hysteresis loop. Right. So what is physical significance of this hysteresis loop? It gets that when a ferromagnetic material subjected to external magnetic field, it get magnetized and it get demagnetized. So at this point it get magnetized, that property we are calling retentivity. Retentivity what? Even in absence of external magnetic field, even magnetic field lines are remain in ferromagnetic material. Right. And amount of reverse magnetic intensity required to remove that magnetic field, that property we are calling corrosivity. Corrosivity is such a property, it protect from demagnetize the material. Fine. See here, in this region OB, this we are calling retentivity and this we are calling corrosivity. Again, this we are calling retentivity, what are calling this? Corrosivity. So this is what concern to hysteresis curve. The question is, what is mean by hysteresis? What is mean by hysteresis? And what about this loop indicates? What about this area indicates? That we will see. Look at me here. So let us see what is mean by hysteresis. Meaning of hysteresis, that we will see. Look at me. So this is nothing but positive H. I can call this is the minus H. So this is plus H, then plus I, this we are calling minus I. Look at me. Question is, what is mean by hysteresis? Hysteresis. See here. Actually, hysteresis is a property of ferromagnetic material. It is a property of what property? If a ferromagnetic material subjected to external magnetic field, it get magnetized. Here the relation between applied magnetic field and magnetization, that we are calling hysteresis. What is meaning of hysteresis? That we will see. See here. When current increases in one direction, how the variation of magnetic intensity and magnetization. So magnetic intensity and magnetization, they will follow this path, right around in this curve, right? If you decrease the current, so how the curve is following? The curve can be following the path AB at B point. At B point, magnetic intensity 0, but magnetization never 0. Magnetic intensity never 0, but magnetization is magnetic intensity is 0, but magnetization never 0. So at this point, even in absence of external magnetic field, magnetization exists. It shows that the magnetization is lagged behind. How it is lagged behind? If reverse current is increased, at a particular point C, I is equal to 0, but H is equal to not 0. So at this point, even magnetic field lines are remaining in ferromagnetic material. Even H is equal to 0. How to remove this magnetization? If we apply reverse magnetic intensity at a particular point, magnetization becomes 0. Magnetic field lines are completely removed from the ferromagnetic material. Then at this point, the ferromagnetic material get magnetized. At this point, ferromagnetic material demagnetized. During magnetization and demagnetization, the magnetization is lagged behind. How it is lagged behind? So even in absence of magnetic intensity, magnetization remain. It lagged actually. Even it is 0, this is not 0. At this point, if we apply the reverse magnetic intensity, then magnetization is 0, but magnetic intensity not 0. Then from this, during magnetization and demagnetization, the magnetic intensity is lagged behind magnetic intensity. If magnetization is lagged behind magnetic intensity, that process we are calling hysteresis. Here what is hysteresis? The magnetization lagged behind the magnetic intensity. So this process we are calling hysteresis. What is hysteresis? Lagging of magnetization with respect to magnetic intensity. This we are calling hysteresis. See here. This hysteresis curve indicates how much energy can losses. When a ferromagnetic material subjected to series of changes, here energy can losses. How the energy can losses? At some other point the material get magnetized. At some other point the material get magnetized. At some other point material get demagnetized. At B point and E point material get magnetized. At the point C and at the point F material get demagnetized. During magnetization and demagnetization, some amount of energy can losses in the form of heat. So that we are calling hysteresis loss. Here we can define one more term. That term is nothing but hysteresis loss. Hysteresis loss. What is hysteresis loss? When a ferromagnetic material subjected to series of changes, it get magnetized and demagnetization. During that, energy can losses in the form of heat. That loss we are calling hysteresis loss. One thing. And how much area of this loop, that much amount of energy can wasted. That is, amount of energy can wasted directly proportional to amount of area enclosed by hysteresis curve. More the area of the hysteresis curve, more the amount of energy can losses. See here, directly what I can call? bigger the area of this loop, more the energy can losses. Directly I can call the energy loss is directly proportional to area enclosed by loop. Directly proportional to area enclosed by the loop. More the area, more the energy can losses. Look at me. The amount of energy can loss directly proportional to area of loop. More the area, more the energy can losses in a ferromagnetic material. See here. Before that, we'll see the one more phenomena here. Phenomena is the property of ferromagnetic material. When a ferromagnetic material subjected to external magnetic field, after removing the external magnetic field, either magnetic field lines are remain or magnetic field lines can exist. On that basis, ferromagnetic material can classify into two categories. One we are calling hard ferromagnetic material and soft ferromagnetic materials. Hard ferromagnetic materials mean if you apply external magnetic field to ferromagnetic material and that external magnetic field is removed, even then magnetic field lines remain in ferromagnetic material. Those we are calling hard ferromagnetic materials. Example for hard ferromagnetic material is nothing but alnico. What is alnico? When a ferromagnetic material subjected to external magnetic field, if you remove the external magnetic field, even when magnetic field lines are remain. So that we are calling hard ferromagnetic material, and all the hard ferromagnetic material nothing but permanent magnets. So this I can call permanent magnets. Permanent magnets. I mean, what is meaning of permanent magnets? Permanent magnets meaning is, once you magnetize the ferromagnetic material, it retain a long time ferromagnetic property. That we are calling permanent magnets. The material which retain ferromagnetic property for a long time if you once magnetize that ferromagnetic material. So those we are calling permanent magnets. Permanent magnets mean once if you magnetize the material, that material retain ferromagnetism for a long time at room temperature. This we are calling permanent magnets. And to be a permanent magnets, some conditions are valid. Conditions are, for a permanent magnet there must be high corrosivity, high retentivity. High corrosivity mean, so once you magnetize it never demagnetized. Retentivity mean once you magnetized that magnetic property remain for a long time. So that for a ferromagnetic material condition must be, the permanent magnet condition must be they have high retentivity. And second condition, so they must be have high corrosivity. What is meaning of this? Once you magnetize, that magnetic property will remain for a long time. What is meaning of this? Once you magnetize, it never demagnetized. That nothing but high corrosivity. And condition must be, they must be have high magnetic permeability. They must be have high magnetic permeability. They must be have high magnetic permeability. These are the conditions for permanent magnets. What are the conditions for permanent magnet? Permanent magnets mean the material which retain long time for ferromagnetic property at room temperature, that we are calling permanent magnets. So permanent magnets are alnico. Alnico mean combination of aluminum, nickel and cobalt. So these are the conditions. But we can make a material as a temporary magnet. We can make the material as a temporary magnet. How to make? If a current carrying solenoid is there, in that current carrying solenoid, if you place an iron, that iron is temporarily act as a magnet. Those we are calling electromagnets. Electromagnets mean the material which temporarily act as a magnet when it is placed in an current carrying solenoid. Those are called as electromagnets. That we will see. See here. Electromagnets that we will see here directly. Electromagnets. Electromagnets. See here. What are the electromagnets? When a magnetic material or when a ferromagnetic material placed in a current carrying solenoid, it acts as a temporary magnet. Those are called as electromagnets. For electromagnet, there must be condition. They have low corrosivity, low retentivity, and must be high magnetic permeability. See here. The condition for electromagnets are they must have low retentivity, corrosivity, and have high magnetic permeability. High magnetic permeability. I mean, so if a soft iron placed in a transformer core, it has magnetized easily, it has get demagnetized easily, and more number of magnetic field lines are passes through it. So that generally electromagnets we are taking soft iron. Soft iron is nothing but a best example for electromagnets. This soft iron has a low retentivity, low corrosivity, and high magnetic permeability. Due to that reason, the soft iron are used in a transformer core because it get easily magnetized, and it gets easily demagnetized. It has a low retentivity and a low corrosivity. Low retentivity mean low retentivity mean what? Even in magnetic field is applied, all magnetic field lines are removed. Low corrosivity mean when magnetic fields are removed, it easily get demagnetized, and it has high magnetic permeability. Due to that reason only soft iron it is used in transformer core. Then where we are using the electromagnets? The electromagnets they are used in cells. They are used in cranes to lift the huge amount of iron from the earth. And they are also used in telephone diagrams. So some few uses are there for the electromagnets. They are used in electric cells, they are used in telephone diaphragms, they are also used in cranes to lift the huge amount of iron from the earth surface. So these are few uses of electromagnets, and these are the conditions for electromagnets. How a ferromagnet act as a temporary magnet? Directly we can call electromagnet being temporary magnet. How material becomes temporary magnet and what are their conditions? So this is concerned to hysteresis curve, meaning of retentivity, meaning of corrosivity, hysteresis loss, and amount of energy losses during a ferromagnetic material subjected to series of changes. So up to here magnetism and matter chapter has been over. So we'll see next chapter in the next session. Thank you.